Hi guys, welcome to this demo session where I will show you how we at Stream Analyze would implement a typical automated vision pipeline demo. Before we start with the demo, I'm going to give you a really quick rundown on what we at Stream Analyze do, just so you have some background on our company and product. So Stream Analyze is we develop and maintain a platform for easy to use developing, deploying, running, and managing analytical AI models on massive fleets of distributed edge devices. We can process any type of data, be it sensor data, images, audio, or video. You will see an example of video and images today. And one thing that we do really focus on is that we try to bring the convenience of the cloud to the edge. And that means that we actually allow you to work interactively and do continuous improvements on your models on edge devices without relying on expensive and risky firmware over-air updates. And we also try to keep a very high level of abstractions for our users using a declarative computational query language, which allows us to what we call democratize edge AI, meaning we make it very much easier to access these edge AI models using our system than you would do with regular IoT projects with programmers. A generic setup of our system or Stream Analyze platform looks like this. We have to the left here, we have the assets and sensors where we install our SA engine, which is our core technology, and we have several of these assets connected maybe to several sensors connected to one asset, and all of these assets can then be connected to either a private or public cloud or on-prem depending on the use case. Then on the top right here, we can see that users like data scientists, analysts, and engineers or product developments, they use SA Studio, which is our VS Code integration for writing queries and developing and deploying AI models to edge devices. And what you get back from them is result streams. But you can also add on bespoke UIs, such as we showed you today. We'll show you how we can use GitHub Actions to integrate automatic workflows into Federation services as well, for instance. We will also show in the demo now that we have what we call SA staging. So when working with these kind of operational technologies in the field, it's very important to test and validate the models that they are performing according to specs before deploying them. So that's why we supply a SA staging environment, which essentially is a copy of the production environment, but we can run these models on either a small set of real devices, simulated or emulated edges to test the models before you deploy them to make sure they're actually doing what they should. I'm going to do a very quick thing about SA Engine as well. SA Engine is our core technology. You could say that SA Engine is, if you can ask us what we're proud of, what we put most time into, it's SA Engine that's been in development and research for many decades. Of course, we don't have the same code base as back then, but it's been evolved over a very long time, going from a object-oriented database to a data stream management system to now a fully embedded edge analytics AI platform essentially. And inside the system, we have a main memory database, a data stream management system, a computation engine, and an inference engine. The core system only requires a C99 compiler, and it requires in the non-runtime you see here, which is the one executing the queries and the models, only requires 17 kilobytes of RAM. So what happens is a user interacts with the SA Engine by writing computational queries, and these queries are first optimized using our patented optimizer. And once you have an execution plan, we give that to our dynamic compiler, which is then compile this down to machine code, which allows it to execute then as assembly code on the target edge device, which means that we do get the high-level computational query language, but we're getting the compiled language speed, which is a very good thing with the system. So in this demo, I'm going to show you a traditional vision pipeline with SA Engine. We're going to start with an edge deployment. I'm going to run this on a Raspberry Pi with a Coral TPU connected to show you how we can utilize like accelerators on the edge as well. Once we deploy the edge there and run the initial model, we will start creating continuous queries for finding significant data. And what this means that we're gonna do with the data, we're gonna fine tune the models based on this significant data collected from the edge specified as continuous queries. And an important part here is that these queries can be defined and redefined on the fly, and it means that over time, as your needs change, you can change the queries you run and collect using our system. I hope that'll be clear during the demo as well. After that, we're going to use my PC here as a client and as a studio, and I'm going to use SA Engine to connect to the Federation, collect data that collect only the interesting frames that the edge emits. And we're actually going to do automatic labeling using YOLO V8, a much more powerful network. Oh, by the way, on the edge here, we're going to be running the SSD Mobile Net V2. And up here, we're going to use YOLO V8. So we're going to take the frames that we deemed interesting or significant from the edge, We're going to classify them using YOLO V8, and if the classification from the YOLO V8 differs a lot from the one we got on the edge, we'll add that to our fine-tuning data set. And in this case, we'll call these labels an elephant, just to try and make me become an elephant in the fine-tuning network, to show you that we are actually updating the network during this process. Once we collected and labeled the data, we will trigger a GitHub action, which will then start fine-tuning on a regular PC with a GPU, which will be training, which will be a self-hosted GitHub Actions runner. And it will fine-tune the model, and once it's fine-tuned, we will deploy it to a SA engine in staging, which a edge in SA staging, which will do validation of the model and make sure that we find the elephant in the room. And once we found the elephant in the room, we'll deploy the fine-tuned model to the edge. That's what we're going to see today. And let's start with these two points. We're going to deploy the initial model, the SSD MobileNet V2, and we're going to run it and show that it's using the TPU on the Raspberry Pi. So first of all, we're going to look at some metadata. We're going to have an edge called the Vision Edge, and if we run this, we can see that the Vision Edge belongs to the Vision Demo group, and we can see here that the Vision Demo group right now does not have any models. So we're going to start here by manually creating an initial model we're going to run on our edge devices, and then we're going to fine-tune it and redeploy it, and then we're going to see that updates as well. So, in an automatic fashion. But first, I'm going to do this manually here. So we're doing this. It's going to create 2 releases and upload them to the. Oh, okay. So let's see here. Let's do 1.82 then. Sorry there. So there we go. Now we're uploading the model to the Federation services. And I'm going to bring forth my Raspberry Pi here. And we're going to go like this, and we can start the SA Federation Services Edge here. What you see then when it's connected, you see it actually starts downloading both the MobileNet SSD model here, and it's going to start downloading the Vision Pipeline model here as well, 1.82 there. So now it's installed 2 models, and it started running. I'll remove this, and we can see that it's running by being able to look at the object detection results here. So now we're going to run this query on the edge. So we're going to run this on the Vision Edge. We're going to plot it as a bitmap, and we're going to view the annotated object detection. And we can see that it's actually running a model called MobileNet, TPU-MobileNet, and you see it's classifying me as a person. And if we move around, you can see stuff happening right there. So now we're actually running the model. And just to show you how easy it is to get this kind of integration done with a Google Coral TPU and using so when you're running Vision pipelines, you're usually running these larger Linux-based devices or devices that actually have some Python on the camera interface. That makes it super easy to integrate, because then you can just do a core integration. You can use these, I think it's 27 lines of code. Essentially, you have 2 Python functions of loading the model, and then a function taking a frame and doing the inference of it, doing the invoke the model, the interpreter. And you just need to define 2 functions in OSGL saying that this is a Python function in this Python package, and this is name, and this is the Python package, this is names. It is a super trivial integration. And so now I showed you the first 2 parts, 1 and 2. They're done, and they were run here on the edge device, as Eric mentioned as well. And now we're going to do a look into the meat of the project, or this is going to be the most manual part. We're going to create a non-trivial metric that will monitor consistency of the classifications over time on the edge. And this is, the continuous query finding significant data. Once we've done that, we're going to collect the significant data from the edge for fine-tuning centrally. And once we've collected data, we're going to do some automatic labeling using YOLO V8. And finally, we're going to trigger the training, which will be the next section of the demo after this. So first of all, we're going to have the edge deployment, and we're going to deploy a continuous query to the edge, which will filter what images we can collect centrally. So we only get the frames that are of interest for this fine-tuning, essentially. And those will go to my user client in the end here. And then we will label it using YOLO V8. So let's go. So before I show you how we define the KPI, I'm actually going to show you the results of what we're going to create. So we're going to do so when I say KPI, it's from an earlier project where they call it Key Performance Index of the model. But essentially, when I say KPI, I think a metric that measures the performance of the network in some way, and it can be the value of that can be significant. So if you want to have when a metric is fulfilled when I collect data. And for instance, here we're going to be using SSIM and Jacquard KPI, which means we're going to actually do first a structure similarity index measurement, image measurement, which is essentially compares two frames in a similar way as a human eye would do. So it actually does a Gaussian blur and then compares the frames. So you don't get a pixel perfect match, but more of a fuzzy match. And a SSIM score of 1 means they're exactly the same, essentially, and a SSIM score of 0 means they differ quite a lot. And it's worth noting that SSIM is a quite computationally expensive operation. So it's you would not be able to run this SSIM model on the edge without our optimizer and compiler. You would have to do it in compile, and you need to compile it essentially to make it run efficiently. You need to have it you need to have the SSIM implemented in a compiled language essentially to make it run on these model bases. And then Jacquard KPI is essentially it's kind of the same type of measurement as for images, but it compares to the bounding boxes. So essentially, Jacquard will compare the bounding boxes of the output of the two frames, and if the bounding boxes differs too much, they will it will be a so if they're the same, the value will be 1, and if they differ, the value will be close to 0, or if they have no intersection at all, the value will be 0. It essentially compares the area, the union area divided by the intersection area. Yeah.
The other way around, I guess. Intersection by the union.
Yes, intersection by the union, sorry. Anyway, so here we can see the KPI running, and if I'm still, you'll see that we're very close to 1, and this is 0.97, so it's essentially 1. For the SSIM, I can, for instance, take my finger here, and we'll see a dip soon. So again, I'm going to go faster. There we go. With a dip, and you can see that we can get a better diff in the Jacquard by just moving my hand, for instance. Now we're getting a bigger reading on the Jacquard index and a much smaller reading on the SSIM, and that's exactly what we want to create for index. We want to get the frames where the classification bounding box has differed a lot, but the image hasn't. You could say that would be like, okay, so if the images stay the same, the frames stay the same, you would kind of think that the classifications should kind of stay the same as well. And if they differ too much, there might be some issue with the bounding boxes for the model, for instance, or something like this. But now, actually, let's go in and create this model here. I'm going to go into our studio. Let's see here. So we're going to do this from our studio in the web interface. And I'm going to show you now how you use the flow editor. It's a way to connect flows and create. Essentially, it's a very nice query builder for doing models in SE Engine. And I'm going to show you how to create a very simple model that's going to run on the Vision Edge first, which will not have anything to do with the image, but rather just a simulated stream. So we're going to take a SimStream box, and we're going to say that we want to have a pace of 100 hertz. You can look at this, and we get the 100 hertz stream there. After that, we're going to add WinAg. I'm going to drag this one here. We're going to do 128 and 10. We can then stop this, and we can start this, and you'll see that we both have this stream here, and we have the window as a vector. Very nice thing with the flow editor when you're developing like models of larger flows, you can actually inspect this. So if you just want to look at the output, you can, but you can also at any time inspect any subflow. So you can see like, okay, this is what goes into the WinAg, and this is what comes out of the WinAg. You can actually kind of like experiment and see. You can actually use this for debugging the model. And I find this very useful for debugging the model, because if you want to step-by-step debugging on a data stream or stream analytics is very hard, because you want to run this over time. So it's much easier if you can visually compare the outputs over time to see what happens. It gives you a very powerful tool for understanding the intricacies of the model. So let's just take this one and then do an RFFT here. And we'll take this here. That's a Fourier transform. And I'll actually just, let's actually take the full one here. Then okay, let's take this first. So this one, and now we have some smartness. So if you have the wrong types into the boxes, we will try to figure them out automatically, and we can just press OK. And now we'll start running the model here with FFT out. And just to finish this small, what I think is kind of fun doing the arg. If you take a Fourier transform spectrum, doing argmax, find the index of the maximum value, and then do a histogram. That gives you a very nice, what I think a very nice fingerprint. So this histogram goes from 10 to 128 with a 128 bins. And then we can run this, and we'll get a very nice fingerprint of the Fourier transform, essentially here. We can see you will see the tops here on the histogram is obviously the tops here in the FFT over time. Nothing specific for this model. For this demo, more is a fun model to do, I think. A very nice part with this flow editor is that once we have this flow defined, I can go here and press OSGL. I can select query. And this was the query that was run on the Vision Edge device. So we actually just created a query that will run there. And these boxes can be user defined. So you can create your own boxes, and they will be added to the list of boxes you can create there. So you can have, power users or like data scientists and engineers or very experts on AI and machine learning, they can create these boxes and allow for like service technicians or OT technicians to use the flow editor to create kind of like who might understand the flow on the factory floor, for instance. They might understand that they want to compare machine 1, 2, and 3's output in some way. They can use this to kind of create these kind of more high-level models without having to use any code. Or you can use it for just debugging the models, which I think is very nice. A very cool thing is that we can actually just remove these things and go in and select WinAg and go here. We're just going to remove some, we're going to change the query and we can press F4. We'll get back to this initial graph here. So we can go from OSGL to the graph and from the graph to OSGL. Yeah, so now let's create the KPI we're talking about there. So I'm going to go into here. So you can see, for instance, I've loaded a model here with the function definitions for this demo, which are then user-defined boxes for the flow editor. I'm going to go here. I'm going to start by taking the object detection results. And then we're going to apply this function here, which is annotate frame from object detection. And this mainly just so give me a webcam here. So hello, here I am again. And now we're going to start by dragging out the SSIM and Jacquard stream here. Both of these will be applied over the object detection results. And so the SSIM will take a frame every half second, I think it is, roughly half second, and it will compare them to each other. And the Jacquard will take the classifications of the same frame every half second and do the Jacquard index on the bounding boxes of the frame. And then you'll recognize these two lines from before. The top one is the SSIM and the bottom one is Jacquard stream. So for instance, if I drag my down here, I can go look with my hands. This usually gives good readings. We usually see bigger readings on the Jacquard index than on the SSIM, for instance. So those are these two. And then we're going to take a function that essentially combines these two, which is here, the SSIM and Jacquard. And it actually takes the SSIM stream and a threshold for that one, say 0.9. So the SSIM should be higher than 0.9. And the Jacquard index, should be less than 0.9. And this will actually it will only emit values when this KPI is fulfilled, or these thresholds are fulfilled. So for instance, now when I'm just sitting still, we're not getting any readings. But if I start moving my hand up here, now we get readings here. So now we can see that it actually gives readings when the Jacquard index is below, well, no, it's below 0.8 even, but the SSIM is always above 0.9 here, for instance. So that's the KPI we're going to create, and then we're going to take a function called emit history on reading, which will take this stream. Let's see here, this one, and go into there. And every time, let's see here, sorry, it zoomed out. So this reading there, and then we're going to take the emission here and put it here. And every time we get a reading from the SSIM and Jacquard KPI, we will emit the object detection results. So let me just clean this up a bit here and go like this, and let's stop it. And just to show you the output, we're once again going to show it as a bitmap like this. And we'll do play here, go over here. This as a bitmap. And if I move my hand up, we get a reading there. So this is essentially what we'll send up to the server, but it will be the image and a record or a JSON object with the bounding boxes. So every time the KPI gives a reading, the data will be sent up. But if I'm not moving or like going down here, you'll see that it stands like that. Okay, so my camera stopped working, but you have me here anyway, so in the screen, so that'll have to do. Anyway, so we're only sending the interesting frames now. And of course, this is one way of doing a filter. You can, of course, use any type of filter you want. Quite advanced and quite simple. You could just say, I want to have the frames when the persons are to the right of the image as well, which would be super easy, of course. And you could do more. You can actually add a separate AI model running through the detection to detect if something's wrong as well if you want. So you can go both how simple you ever you want and how advanced ever you want. But once we've done this now, I'm going to remove these and go like this, layout. And now we're going to press OSGL. Do function and say my consistency metric. Okay. I'm going to take this function that we created here. So this was the model we ran there with the 4 functions connected. And we'll go in here and we go into our Vision pipeline demo and add it here. So now we're going to create this function. We're going to add what we call a new stored edge query here, which essentially says that this ID will be running this function here, my consistency metric. And by the way, here's the object detection function we ran before there. So we had a function running this object detection. So essentially what it creates is, you can see them as creating a model service on the edge device, making sure that the model is always run on the edge. So let's save this, and now we're going to redeploy this model. I'm going to stop this query because it's going to stop working, and we're going to go to run, and we're going to do a 1.83. Create this here, and we can see here that it will start to. Yes, Simon.
Yeah, I was just thinking now when you're saying you're creating a release and deploying it and publishing it, where does that release end up?
The Federation services in the cloud, we do have what we call a model server. So essentially, from my local PC, I take the model, I package it using this create release, creating a package, and then here I'm saying publish this to the model server of the Federation, name it mobile SSD with this version. So that means that a edge can then do essentially a like this model import of mobile net SSD, comma 1.83, like this. So doing this on an edge device would now install this version of the model on it essentially.
All right, got it.
Thanks. And what you saw here, yeah, no problem. So what you saw here was we got the new versions, installed them, and we can now see that actually you can see in the log here that it actually started both the object detection and the MyKPI function. And we can view that, but we can still look at the object detection, which is still there. And we can also look at a subscription here. So we can do here, subscribe. So actually one of the boxes there actually publishes the flows on the SSI Manager card KPI, which we can actually look at it here, and we get the SSI Manager card over time as well. So now it's time to do the recording of data. Or actually, let's just take a look at where we are. So you saw me not do these parts. We've done the continuous query. We've done it using the flow editor. You saw you can create a quite advanced metric that we then generate a function for, deploy to the edge again. And now it's actually running a filter, so we can actually look at the MyKPI for outputs of frames of interest now. That's what we're going to do. We're going to actually do we're going to essentially connect a client here on my PC, and it's going to subscribe to the MyKPI stream of the edge. And once it comes data there, it's going to sort it and do the labeling using YOLO V8, as I told you before. That I'm going to do like this, and I think that's the GitHub runner. We're going to go here, Sage Vision pipeline, go like this, and we're going to do a downloader. I'm going to go so you see my camera as well. Same time, sorry. So we'll do like this. So run the downloader. In this case, we're going to run and download only 20 frames for fine tuning. I've also collected around 200 frames before this demo, so we get some training data. But in a real life environment, this would probably be running all the time. But maybe for a demo to show you here, I will just show it a one shot. As a one shot. So running this, now it's going to load some stuff, and now it's connecting the Federation, and now it's actually loading the YOLO V8, and it's going to take a few seconds, but once it's loaded, we're going to start seeing some frames coming. I'm going to start moving here. Here we go. So now it's collecting frames here. This is the output from the YOLO, and we got 10 of it. So I'm going to start moving a bit. La-di-da-di. Just triggering the readings here. 16 frames, 17, 20. There we go. So now the collection was done, and we have exited, and we triggered a deployment or a GitHub action. So we go here. Go to this one here. There we go. We can look into train, and that's now we've actually started the final step. It's going to take about 3 minutes. I'm going to first start. So we did the 3, 4, and 5. Now we're going to do the fine tuning using TensorFlow. Then we're going to validate the fine tuned model using SA Engine and TensorLite on a simulated edge in SS staging. And you will then see an immediate deployment of the model and update of inferences done through the model from VS Code as well. So we're going to see this it will just be done automatically from now on. We will include these 3 parts. We'll do the fine tuning. We'll do the validation of the model post quantization. Once it's validated, we will deploy the fine-tuned model down to the edge device. And now I'm just actually gonna set up the screens here. Yes, Eric.
So after this fine tuning, you will also perform a quantization of the model.
Yes. That is done by TensorFlow, by the way. So yeah.
Right. And then you validate using the data you just collected, along with some additional data.
In this case, you would probably have a bigger data set. In this demo, we're using the fine-tuned data and make sure that we find an elephant in the room in that data. But right. Of course, the fine-tuning, you would have a separate validation set in a more production environment. But for demo purposes, we're using the same images in this case.
Right, got it.
So you can see here that it actually trained here, did the fine-tuning of the network. And now it's translating it to TF-Lite and quantizing it and compiling it for the TPU as well. And when this thing is done, it's going to go quite fast. So then you should keep track of what happens both here on the Pi when it starts deploying and on my classification here. You should see, and the name of the mobile net there. That's the where the final part will happen. In a few seconds.
Are you going to interact with the system in any way during this deployment?
Nope, my hands are here. So now it's full automatic. So
nice.
I would say, like, I think the note here, both the training we did at TensorFlow, for instance, and the labeling with YOLO V8, that could be used. You could use like there's a lot of systems out there doing these kind of things. So you can of course utilize these kind of systems for both labeling, like Label Studio, and training. You could use both, TensorBoard, TensorFlow, PyTorch. There's a dime a dozen companies. So almost every silicon manufacturer has their own kind of training system for fine-tuning networks. You use that as well there. So it's very compatible with like any type of training system there. And they usually output like an ONNX file or a TF-Lite file, which we then can run using our integration with Python on the Pi easily. So now we're validating. Now we're actually doing a small validation that the quantization worked in the TensorFlow training fine-tuning. So this you can call this a pre-validation before we validate it in SA Engine. So this just makes sure that we did the model worked as expected in TensorFlow, and now we're going to test that it works as expected in SA Engine, which is done now. I think test model there, and you'll see we found the elephant in the room. Yeah, now we're deploying it. You'll see here we'll get a any second now. Any second now. There we go. There we got the new model, and you'll see now that we started getting elephants there. So yeah, and we're on the model in the 2 now. So we did deploy the fine-tuned model. We never stopped a query. We never lost a frame, and we did it in full operations without any restart at all. And of course, you'll see this model actually works quite bad. You can very many elephants here, mainly when my hands are up here, because if you recall, like I moved a lot up here when I collected the data. And we do need to get elephants, but I would not call that an improvement. So let's actually just revert this. One second here. So let's just do this P here, Vision Edge, and just say, okay, we want to revert this. So set TFL model to run, and let's set that to the old one, TPU mobile net. Oh, whew, now we're back. Reverted, crisis averted. We can redo our fine tuning and try to figure out what happened there. That's very nice. So yeah, exactly. So that was that part. Now you saw us do all of these 8 points. Just a quick recap what you saw. You saw us running and deploying and running a MobileNet v2 object detection, actually by using the TPU on the edge on the Raspberry Pi. You saw me creating a continuous query for finding significant data using the Flow Editor and OSGL. You saw me collecting the data, and you didn't see the automatic labeling using YOLO V8, but you saw us doing something with the data for starting for fine tuning. We then triggered a GitHub action, which started the fine tuning and generation of the new fine tuned model, which we then validated, and we found the elephant in the room. And lastly, you saw us creating the release. And if you weren't fast enough, but if you were fast, you also saw how we could then get an elephant as a classification here of me in the Flow Editor or in the VS Code instantly. So what you've seen is a complete end-to-end vision pipeline, or at least a version of how you can do this with SA Engine. We had YOLO V8 for object detection and labeling centrally. We had SSD MobileNet v2 for object detection on edge. We did a continuous query for identifying and collecting relevant data on edge. And I cannot press enough that these, as your models evolve over time, the data that you need to fine-tune them becomes more and more scarce. So we've seen a lot of customers in automotive or AD and ADAS systems where the key for getting their models better was how smart could they be with the data collection. So the smarter you can be with data collection over time, the better you can improve your models over time as well. Because no car or truck manufacturer has all of the data for a 10-year-old truck when the truck is released, because it's only been there for a year. So you will need to do this as in production, essentially. You saw me using a very compact and easy specification for edge models and queries, both the no-code Flow Editor, and you did not see exactly, but you saw some part of it where you can use the highly efficient computational query language for implementing these kind of metrics. I showed you a trivially simple integration with like any accelerated inference runtime available on edge. You saw the Coral TPU information was 14 lines of Python and 4 lines of OSGL to integrate them. And I would say like it is as trivial to integrate with any other runtime that has either a Python interface, and it's as simple as for the CPU. If it's a C or C++ interface, it is as simple for the C or C++ language relative to how simple it's for Python. So of course, there's more work for a C integration, but that will be a C programmer doing it, and for him it will be trivial, so to speak. So it is a very mature and well tested and well and battle tested interface for doing these kind of integrations, which works very well. And we've done all of this while keeping a high level of abstraction and a C-level efficiency of the models that we run in the query language, which I think is very cool. That you actually get this very high level of specification, what you want them done, and you get them as fast as that you would hire a team of C developers to deploy this. That is a really cool thing, I think. And you saw one thing you saw as well, interoperability with many other systems and packages such as VS Code, GitHub Actions, TensorFlow, TensorFlow Lite, OpenCV with that for using the camera, and of course you also saw Python out there. So we use that as the Raspberry Pi comes with that, and it's very easy to use. So thank you for the demo. Now we can have a Q&A.